Okay, so today, we got two topics today. One of them, whoops, let's go back a bit. Let's start there. So I'm going to talk about two things today. They're two pretty quick things. When we ended previously at 3256, when I talked about how when you do an ANOVA, like an example in our quiz here, we have four treatment groups here, right? There's a 3 degrees of freedom. If we got a significant ANOVA, and I believe with 3 and 16 degrees of freedom, 4 would be a significant difference, it just tells you two groups are different. It doesn't tell you which two groups, or maybe all four are different. So what you do in that case, because the null hypothesis, remember, is mu1 equals mu2 equals dot 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 equals mu k. So what if I want to know which one differs from which? So let's say you've got a significant F. Now what? There we go. Oh, I didn't reveal the slides. Literally what I was talking about. So the null hypothesis is that mu1 blah blah up to mu k. But it doesn't tell you which means differ from each other. It just tells you at least two are different. Because the alternative to that is at least two are different, right? So which two? Well, the first way you can approach this is by basically doing a t-test between the groups, doing t-tests between the groups. But if you did that, the alpha level would go up, right? Or sorry, go down, have to go down. The overall alpha level would go up if we just use 0.05. Because if we had 0.05, you did 5 comparisons. Well, the alpha level is going to go up. Okay, we don't want that. So what's called, there's a correction called the Bonferroni correction, or the Bonferroni T procedure, named after some guy named Bonferroni. Bonferroni's delicious. Do you like that, Bonferroni? Okay, obviously. Some of these are jokes. They aren't good jokes, but they're jokes. They're just barely jokes. So the Bonferroni T procedure takes care of this. By the way, I'm going to show you a bunch of formulas that you will never do this by hand. Like, no one does these by hand. What you do is when you do the ANOVA procedure in SPSS or PSYC or JASP or whatever you're using, you click a little box that says post hocs, and it just does them. So I'm going to show you these to get you the conceptual notion of how they work, but don't worry about actually having to know a formula. I'll point out what I think is important in these things, but no one does these by hand. Like, literally nobody. They're done by hand by people who are trying to be mean to stat students in classes. So it's 1 over n times alpha, where n is the number of corrections. So if we're going to do 3 t-tests, it's 1 over 3 times alpha. Our alpha would normally be 0.05. So now it's 1 over 3 times 0.05. So that's, in other words, a third of 0.05. Okay? This used to be a really big deal because you'd need special tables for this, because it turned out that there couldn't be a table of every possible alpha level. Now we just do, like I said, we do it in a computer, we can do it called clicks, and it's no big deal. So this is your t-testing. We're going to call it t prime. That's what this little tick mark is here. It's a prime. So x bar 1 minus x bar 2, that's whatever the two means are you're interested in, divided by 2 times the mean squared error, divided by n and the square root of that quantity. It's just a t-test. Mean squared error is just an estimate of variance. That's all it is. So why not use it? We have it there. So really, this is literally a t-test. That's all it is. It's just using the square root of 2 times mean squared error over n, little n. Little n is the number of subjects per group. Okay? That's all it is. So if you have 4 groups, you have we have 12 possible comparisons. No, 4 choose 2. It's 24, 12, 6. You have 6 possible comparisons. You probably don't want to do 6 comparisons. You probably want to do maybe 3. Like I said the other day, if we had a situation where we have 4 groups, and one of them is an experimental group, and then we have 3 controls, you might just want to just do 1 comparison. Because you might look at the control groups and say, they're all the same. Let's just compare it to one of the control groups. So you might just be doing 1 comparison. You might want to compare, excuse me, all the control groups. Well, all 6. It's possible. Right. So there's 6 comparisons, right? Is that right? Group 1 to 2, 2 to 3, 3 to 4, 1 to 4, 4 to 3, 4 to 2. Yeah, there's 6. Should we use 4 factorial over 2 factorial divided by 2? Yeah. It's a pretty simple procedure. The thing, like I said, I want you to take note of is we're going to use mean squared error as an error term, and it's a t-test. So here's another one, the studentized range. It's another freaking t-test. It just, instead of using 2 times mean squared error, it's using mean squared error. And this allows you to compare all possible, this is when you do all the comparisons. So this is, let's say, you're going to compare all 6 means in that case. The larger one minus the smaller one, that's the L and the S. And it gives you what's called a Q value. The statistic here is Q. You never report this, by the way. When you're reading a paper, you will never see someone say, and the Q value, they just say, we compared it using student test, and we found these means different. So a lot of times you'll see a graph in the paper, and it'll look something like this. So it'll, let's say we have this. Let's say we have 4 groups, and there are 3 control groups and 1 experimental group. What you would see probably is you would see this, and it would just have an asterisk for each of them, and then in the figure caption, it would say means with an asterisk are significant. You would never report why, because basically the idea is you should be able to get that from the things that are reported. Because when you report an F value in a paper, you tend to, very often you'll even report the mean squared error. So it's all there. So somebody, if they had to, could redo it. Okay, so this is how that works. Then there's the Newman-Cool's test. And you went, wait, what? All we've done here is we've rearranged the student test. Okay? We've rearranged things, and we come up with this value. So we look up a critical value. That's what Q with R. R is the size of the range. Okay? So any set of comparisons with range R. So how big do they have to be? So what you do is you take a look and see what's the smallest difference I'm interested in when I look at my data. So you look at your data after you think it over, and you say, okay, anything that's bigger than 3 different from each other. So you put 3 in there. So you'll actually look it up. This is a value that you look up from a table, the Q value. Then you multiply that times the square root of mean squared error over n, and then you get a value called W sub R. That just tells you how big the range has to be. So you actually come up with a number, and it says anything different by, let's make up a number, 7, those means are different. Okay. It's a very common one. I've used this one myself. But I honestly, whereas most things I know offhand what the formula is, because I use them enough, I don't know the formula. Nobody knows formulas for these things. They're not the kind of thing that you just have to tip of your tongue. It just doesn't work that way. So all comparison range of 3. Did I just say 3? Did I say 7? Doesn't matter. Look it up. Go from there. There's another test like this called Tukey's HSD. HSD stands for honestly significantly different. Tukey was the guy I told you about the term exploratory data analysis. And Tukey has a similar thing. He just says, always make it the biggest possible one. So if you've got one group that's 1 and one group that's 10, then it's a range of 9. Okay. So I'm just showing you some. There's all kinds of other ones too. There's a Chaffee's test. I didn't tell you what Chaffee's test, other than to say no one uses it because it's so conservative a test that sometimes when you have a significant ANOVA, it still tells you none of your means are different. And that seems like something you don't want. Which one should you use? And people ask that because it's a good practical question. Which post hoc test should you use? Most people do all of them. You shouldn't do this. What most people do is they get the data, they try any possible one, and say, which fits with the hypothesis I'm using? And that's why one of the many reasons the post hoc tests bother me is that. I've often thought, and this comes from my old staff prof in grad school, Ian Spence, and he used to say that if you're interested in two means being different, just test those two means being different. Why did you do an experiment with all these other groups? That usually falls on ears that can't hear very well. I've tried saying this, for example, with one of my honor students, and I tell them, just do that, and I get the same thing. Well, everybody else says do it, okay, fine, do that. I don't like it, and that's probably just because the influence Spence had on my development as a scientist. I'd stick to one kind in a paper. It raises a few red flags when you're reviewing an article, and you look at it, and in experiment 1, they did a Tukey test, and experiment 2, they did a Newman-Cool's, and experiment 3, it's like, I think I know why you did that. And typically you'll see that. I've used HSD usually. It's the most, I found it's the best, the best compromise between being conservative, because I want conservatism in my tests. In my statistics, and science should be conservative, because you're making statements about the natural world, you want to be conservative. But you don't want to be so conservative that nothing ever gets discovered. So it's, to me, Tukey's HSD is a nice compromise between being conservative, but not too conservative. So again, these are small things. I wouldn't get too worked up over post hocs, just as a rule. Any questions, though? Do you have any questions that I can answer about post hoc tests? Like, if I was to ever ask you what a post hoc test was, all you say is a post hoc test is a procedure carried out to determine if there are differences between specific means in after you've done an analysis. And they all use mean squared error as an error term in basically a riff on a Ttest. They're all just riffs on Ttest. They really are. All right. So that's not so much.